Hi, welcome back to the channel. In today's lesson, we'll see the simple harmonic motion of a spiral spring. I will show you how to derive the equation for the acceleration and also how to derive the equation for the period of the spiral spring under a simple harmonic motion. At the end, we'll use a simple example to introduce you to how to solve questions relating to simple harmonic motion with the spiral spring. That said, let's get started. Welcome. If I have a spring freely dangling without any reaction, the spring has its full characteristics. Now, but the moment I attach a weight to it, let's say this weight has a weight mg, the mass times acceleration due to gravity. Now, for this body to be at equilibrium, there's a repulsive force from the string. And obviously, for this body to be at equilibrium, the force from the spring minus mg will be equals to 0. So that the force from the spring will be equals to mg. And the force from the spring itself, from Hooke's law explains that the force from the spring is directly proportional to the distance e, this distance stretched by the spring. And obviously, F is the same thing as ke. So that we can conclude that mg will be the same thing as ke. If I need to extend this body a little bit, such that we now extend it through the point X, I have a little extension, and now extend it by X, such that it oscillates, so that the body can oscillate. At that point, the body begins to oscillate, and there's still a force in the spring. But at this point, the body is not actually in equilibrium, so that there's a repulsive force from the spring. At that point, we can conveniently say that the repulsive force from the spring becomes ke plus x. That is, the F from the spring becomes ke plus x. Now, the resultant force from the system, F, the resultant force from the system, F, becomes mg minus k into e plus x. So that F now will be equals to mg minus ke minus kx. And F now will be equals to mg minus, remember that ke has been defined also as mg minus mg minus kx. So that F, in place of F is the same thing as ma. Remember that force is the same thing as mass times acceleration, will be equals to mg minus mg gives way. Then I now have ma is equals to minus ke minus kx. So that a is the same thing as minus kx all over m. Now that's how to calculate your acceleration, the acceleration of the system in a simple harmonic motion. Now, but let's remember that from our simple harmonic motion, let's remember that W squared is the same thing as K over M. And also, let's remember that W, which is the angular frequency, is the same thing as 2 pi F. And F is 1 over period, which is T. So that W is the same thing as 2 pi over T. Now, if W is the same thing as 2 pi over T, and W squared is K over M, obviously I can say 2 pi over T all squared is the same thing as K over M. So that your 2 pi over T all squared is K over M, then 2 pi over T is the same thing as the square root of k over m. And so that, let's invert it. T over 2 pi is the same thing as the square root of m over k. So that t, invariably, which is the period, is the same thing as 2 pi times square root of m over k. Now, so we've gotten our formula for the period of a simple harmonic motion, and likewise acceleration of a simple harmonic motion. Our example says a mass 20 grams is suspended from the end of a spiral spring whose force constant is 0.4 newtons meter. The body is set into a simple harmonic motion with an amplitude of 0.2 meters. Now, the first thing I want to do is I want to convert the mass. My mass is equal to 20 grams, and my 20 grams is something as 0.02 kg. 0.02 kg. So that the first thing is for me to find the period. Remember that from our formula, we got that the period is something as 2 pi, the square root of m over k for a simple harmonic motion of a spiral spring. So that my t now, from here, will be the same thing as 2 times pi, the root of 0.02 over 0.4. Now, from my calculator, that will be 2 times pi into the root of into 0.2236 times 2 times pi, that's 3.14. So that my t from here is the same thing as 1.404. Period is in seconds. Now, for the frequency of the motion, that's f. F is something as 1 over t. That's equal to 1 all over 1.404. So that f is equal to, that's 1 all over 1. That's 1 divided by 1.404. F will be equal to 0.71 in hertz. And for the angular speed, W is something as 2 pi f. 2 pi f, that will be 2 times f, 2 times 3.14 times f, 0.71. That's the same thing as for my calculator. That's times 2 times 3.14. That's equals to 4.47. Now, the last part of the question is for the total energy. You get your total energy KE. The total energy will come from half KA squared. So if you impute half KA squared, K will be the same thing as half times 0.4 times 0.02 all squared. So you can get this straight from your calculator.